Hi guys, good evening.
Sir, good evening, sir.
Good evening, Arunachalam. Okay, good evening everyone. So let's begin our lecture. So in the last class, we looked at the steepest descent method. Steepest descent method, in which we said that essentially the new solution is obtained by starting with the old solution, but then again we go a certain step size alpha n in the direction of the residual, right? So that's what we said. And so while in the steepest descent method, the convergence is guaranteed. Convergence is guaranteed. However, it is slow. Okay, we mean slow because what happens is that steepest descent method actually oscillates in the local neighborhood of the root. Okay, so as we get closer to the root, the steepest descent method actually shows oscillations, and as a result, it will take several iterations to converge. Several iterations to converge. Okay. So this is not a good thing because we want to converge and find a solution as quickly as possible. What happens is that the steepest descent method keeps taking steps repeatedly in the same directions, that it has taken earlier. What does it mean? It means that if it has taken a step in a particular direction, okay, and then it's going to take some step that is kind of perpendicular to it in the next iteration, because we have seen that essentially Rn plus 1 is orthogonal to Rn. But then after some iterations, again, it would basically come back and take a step that is in the same direction as before, okay, as this one, and then it will take a step in this direction and so on. So as a result, it basically keeps taking steps in the same directions. Rather, that means rather it would be nice if we can take rather. It would be nice if we can take a step in a particular direction, by the exact amount that is required, then we don't have to visit that direction again, right? For example, if we were to take, if we had taken a step length of this much length in this particular direction itself, then we don't have to again take a step in this direction. Similarly, if we had taken step length of sum of these two green lines, then we don't have to actually come back and take a step in that direction. So this is what we would like to do, and that is what paves way for another method that is known as the conjugate gradient method. Okay, so this is known as the conjugate gradient method. Okay, so conjugate gradient method is what we now look at. This is known as the CG method. Okay, this is also applicable to symmetric positive definite matrices. Okay, so conjugate gradient method is also belongs to the gradient type of methods. So we are trying to calculate the solution A phi equal to B by minimizing this functional, that is Q of phi, as we have said before. So both, I think maybe in the last class I said Q is not a vector, but Q is also a vector, phi is also a vector, okay, because both of them can be vectors. Okay, so we try to minimize this function and then thereby obtain the solution A phi equal to B. Okay, so this is also similar to the steepest descent method. Okay, however, conjugate gradient method is a little more complicated, little more involved compared to steepest descent method. Okay, now what are these new search directions that we are talking about, that we want to use, right? So earlier we were using the residual as the search direction, but then now we want to use new search directions which are essentially going to be only used once, and we are going to take exact right amount of step length so that we don't have to come back to the direction again. Okay, so these are known as the directions. Let us say we want to call it as D0, D1, D2, all the way to Dn minus 1 or Dn. Okay, where D's are again vectors. So these are all vectors. I may not write the overbar, but we realize that these are all vectors. In fact, whatever I'm writing here are vectors. Okay, and A is a matrix. Right. So these are the directions that we want to use to reach the minimum value on the Q bar, P bar surface. And these are known as the A orthogonal directions. Okay, A orthogonal directions or vectors, A orthogonal directions. Okay, now what are A orthogonal directions? Two vectors, let us say dm bar and dn bar are said to be A orthogonal if they satisfy the following condition. Okay, what is that condition? That condition is dm transpose A times dn equal to 0. Okay, we realize that here whenever we write superscript dm dn, these are only going to denote some particular d. Okay, not exactly d to the power m. Okay, similarly, although I have not written overbars here, we know that these are vectors and A is a matrix. Okay, so if dm transpose A times dn is equal to 0, then we call them that dm and dn are actually A orthogonal to each other. That means what we are saying is that you multiply one of the vectors with A. Okay, that means A times dm. When you take an inner product of A times dn with dm, that is equal to 0. That means the dot product of dm and A times dn is equal to 0. Then we say that essentially dm and dn are A orthogonal to each other. Okay. If it were just orthogonal, this would have been dm transpose dn equal to 0, just like we had Rn plus 1 transpose Rn equal to 0 in the case of steepest descent method. Whereas here we are looking at A orthogonal directions. Okay. So these are A orthogonal directions. Okay. Now, if we can find such directions, then we can calculate our new value for phi, okay, as follows. So we can calculate phi n plus 1 equal to phi n plus alpha n times dn. Okay, so that is how we can calculate the new value for phi n plus 1 from phi n by taking exactly the right amount of step alpha n in the direction of dn. Okay, so that is how we can calculate our new guess value for phi. Okay, fine. So that means let me also define what is error. If I were to define phi as the exact solution, phi is the exact solution, then I can define my error at any time level n equal to phi at n minus phi. Okay. Similarly, error at any level n plus 1 is equal to phi n plus 1 minus phi. Okay. So these are all again over bars. I may or may not write them a little later. So, okay, so this is what we have. So this is the error at nth iteration. This is the error at n plus 1 step. Okay, so that's what we have. So that means from equation 1, I can subtract phi from both sides, which is going to give me phi bar n plus 1 minus phi equals phi bar n minus phi plus alpha n dn. Okay, so this is nothing but e n plus 1 equals e n plus alpha n dn. Okay, so that is how my error relates these two, the previous error and the alpha and dn. Okay, I can also calculate what is residual. Residual at time level n plus 1 is equal to b minus a times phi n plus 1, right? That's what we have. Residual equals b minus phi times n plus 1, but my phi times n plus 1 is equal to, I have from equation 1, what I have for phi times n plus 1 equals phi n plus 1 equals phi n plus alpha n dn. So if I'm going to substitute this thing, I'm going to get phi n plus alpha n dn. Okay, so that's what I have. This is for my r n plus 1. So this is going to be nothing but b bar minus a times phi bar n minus, because alpha n is a scalar, I can, when I multiply with a, alpha n can be either brought before a as well. So this is going to be alpha n times a times bn. Okay, that is what I have for r bar n plus 1. Okay, so that is my residual at step n plus 1. Okay, but what is my b bar minus a phi bar n? This is nothing but the residual at level n. So this is residual at n plus 1 equals residual at n, right? That's what I have. Minus alpha n a times dn. Okay, let me call this equation number 2. Okay, so essentially this equation is now relating the residual at n plus 1's level is basically a linear combination. So residual at level n plus 1 at level n plus 1 is a linear combination of the residual at n and a times dn, right? That's all it is saying, because you have Rn and a times dn. So we are just basically taking a linear combination of these two vectors, and then that is giving you what is Rn plus 1 bar. Okay, so that is what we have obtained. Now, if we want to take a step size of the right length, that is alpha n, then we say that we should be able to, essentially we can calculate, so how much alpha n should we take? You know, what is the step size? To look at what is the alpha n step size, we know that essentially we have to minimize q bar of phi bar n plus 1, right? We have to get to the minimum. So we have to basically look at alpha n such that this is going to be minimum at that location in the direction dn, right? So only if you're looking at a particular direction dn, wherever q bar of phi bar n plus 1 is minimized, that is the location where you want to go in that direction. That means we can calculate alpha n by minimizing differential of q bar of phi bar n plus 1 divided by d alpha n, and you set it to equal to 0. Essentially, we have now posed this as a minimization problem. Okay, so we pose this as a minimization problem, but we already know what was q bar. Q bar of phi bar n plus 1 is nothing but, we have already written this thing. This is phi bar n plus 1 transpose a phi bar n plus 1 minus b transpose phi bar n plus 1 plus c, right? This we already know. Okay, so I can now write what is this thing. So because q bar is a function of phi bar n plus 1 and phi bar could be a function of phi bar is a function of alpha n as we have written here. Phi bar is a function of alpha n as we have written here. So we can apply chain rule and then calculate this differentiation just like what we have done before as d of q bar of phi bar n plus 1, okay, divided by d alpha n can be written as d of q bar of phi bar n plus 1 divided by d of phi bar of n plus 1 transpose, okay, times d of phi bar n plus 1 divided by d alpha n is equal to 0, okay. But what is the derivative of dq bar with respect to phi bar n plus 1? This we have already seen. Essentially, derivative of this guy after applying the derivative with respect to phi bar n plus 1, we said this is basically going to be phi bar n plus 1, right? Or a phi bar n plus 1 minus b, right? That's what we have said in the last class, right? This is going to be a phi bar n plus 1 minus b transpose times what is d phi bar n plus 1 by d alpha n. That means I go back to the definition of phi bar n plus 1. Phi bar n plus 1 is here, right? So phi bar n plus 1. So what would be d phi bar n plus 1 by d alpha n? That is simply going to be dn, right? Because this will be equal to 0 and the derivative with respect to alpha 1 would be this quantity that is multiplying it, that is d bar n. Okay, so I can write d phi bar n plus 1 by d alpha n as simply dn equal to 0. Okay, so this is what we have. Fine. So what is a phi bar n plus 1 minus b bar? A phi bar n plus 1 minus b bar is nothing but minus of b bar minus a phi bar n plus 1, which is nothing but residual at the level n plus 1, okay? And then transpose times d bar n equal to 0, okay? That's what I have. And of course, this minus, I can ignore it right now and then write it as, send it to the right-hand side. So this is going to be r bar n plus 1 transpose d bar n equal to 0, okay? So that means we got a relation by for minimizing this thing, which basically says that the residual at the n plus 1th step is going to be orthogonal to the dn, right? That's what we got. Okay, but then I can write rn plus 1 bar, which we have before, which is basically from equation 2. I can write it as rn bar minus alpha n a dn. Okay, so I can write this as r bar n minus alpha n a dn transpose times d bar n equal to 0. Okay, because after all, we wanted to calculate what is the alpha n, what is the step size I should take in the direction dn, right? That is the motivation with which you started, right? We are doing this thing to calculate step size, that is alpha n. Okay, so this is going to basically give me, if I were to apply this transpose and multiply with the dn, this is going to give me r bar n transpose d bar n minus alpha n is a scalar times this one is going to be a d bar n transpose is going to be d bar n transpose a transpose d bar n equal to 0. Okay. But then we know that a transpose equals a. So from here I can write what is alpha n is the step length we want to take in the dn direction is equal to r bar n transpose d bar n divided by d bar n transpose a transpose equals a d bar n. Okay, so I'm able to obtain what is the value of alpha n. Okay, what is the alpha value n? But then I can only calculate alpha n if somebody tells me what is the direction. So if I knew the directions, so if we know the directions, know the direction vectors d bar n, then we can calculate alpha n. What is the step size we can take in that particular direction? This we can calculate. Now you see here, this is different from what we obtained in the steepest descent method. In the steepest descent method, I think we have obtained this in terms of purely in terms of our residuals, right? Alpha n is obtained purely in terms of residuals. You had something like Rn plus 1 transpose Rn plus 1 divided by Rn transpose Rn, something like that, right? There was no concept of D, right? Because this is a new direction that we are defining. Okay, so let us now look at, okay, so we were able to calculate what is alpha n, okay, given the directions dn. But then how do we calculate the directions dn themselves, right? So we want to calculate, so how to calculate directions d of n, right? So this is the question. Here what we use is we use something called the conjugation, okay, which is basically the conjugate gradient method. For this, what we are actually using here is known as the Gram-Schmidt decomposition, okay, but we are slightly doing it in a slightly different way so that this is not visible as such, or Gram-Schmidt conjugation or decomposition. So what we are trying to do is that we say that every new direction dn plus 1 can be obtained from the residual Rn plus 1 plus beta n dn, okay. So we say that every new direction should satisfy this relation, okay. What does this relation mean? This is actually basically obtained from Gram-Schmidt decomposition or conjugation. What we are saying is that I have, let us say, Rn plus 1 as my direction. So let us say I have, let us say that is my Rn plus 1, okay. This is my R bar n plus 1, okay, direction. But then I have also, I have also what is known as, okay, so let me call this as, no, not Rn plus 1. Let's say this is my D bar n direction, okay. So this is my D bar n direction. Let me take other direction, which is basically, I found a residual. Let us say this residual is something like this, okay. So this is the residual I have obtained for R bar n plus 1. So that means I have nth iteration. In nth iteration, I am working with a particular direction dn, and I have calculated now a new residual at the next iteration, that is Rn plus 1 bar, that is pointing in this direction. But then, as we said before, we don't want to, we want to find a new dn plus 1 direction that is a orthogonal to dn bar, right? That means when you multiply dn bar and a times dn plus 1, their inner product should be equal to 0. They should be orthogonal to each other. Okay, how am I doing that? I am doing that essentially by subtracting off any component that is there in the Rn plus 1 that is in the direction of dn, right? That's what I'm trying to do. So what does it mean? That means I am multiplying my I'm multiplying my dn with some beta n. Okay, so essentially I'm multiplying dn with some beta n. So that is where I am. So this is going to be my beta n times d bar n. Okay, I'm subtracting off any component of that is there in this direction, and then I end up with a vector, right? Essentially that is my Rn plus 1 bar plus bn dn. That means Rn plus 1 plus bn dn. Okay, so bn dn plus Rn plus 1. So that is basically my d bar n plus 1. Okay, so that is my dn plus 1 direction. Yeah, so I could either do this here, or maybe I can even do it at the tip also, maybe. Okay, so this is the new direction dn plus 1. That is going to be a orthogonal to d bar n. Okay, so we are doing this by essentially subtracting off any component that is there, that is bn dn. Bn can be negative, doesn't matter. Okay, so we are essentially subtracting off from the residual Rn plus 1 bar, right? From this residual, so we know that essentially R plus n plus Rn plus 1 is perpendicular to R bar n. This we have already showed in the steepest descent method, right? In the steepest descent method, we said that every residual to take is going to be orthogonal to Rn. That we have already proved. But then now Rn plus 1 has a component that is there in the Dn direction, right? Okay, here, as you can see, there is a component that is something like this. Okay, so that essentially we're trying to remove that component. Okay, by either I can actually even place this B and Dn here also. Okay, so it's going to give me something here. Okay, so so we are essentially removing that component, and then you end up with this new component that is Dn plus 1. Okay, so that is the idea of this Gram-Schmidt decomposition, or essentially calculate the new direction. Okay, Dn plus 1 bar. But then we are saying that this Dn plus 1 bar should be Dn plus 1 transpose should be A orthogonal to Dn, right? So that is the condition we have set forth. Okay, so Dn plus 1 bar equals Dn plus 1 bar n plus 1 transpose equals A times Dn bar equal to 0. But then let me substitute for Dn plus 1 bar from equation 4 into this A orthogonality condition. That is going to give me R bar n plus 1 plus beta n d bar n transpose times A times my A times Dn bar equal to 0. Okay, so that's what I have. Okay, so this is what I have. Okay, so if this is what I have, I can write this as R bar n plus 1 transpose times A dn plus Bn is a constant, it can be taken out, and we have d bar n transpose A times d bar n equal to 0. Okay, so from here I can calculate what is the value of beta n, that is equal to minus R bar n plus 1 transpose A times d bar n divided by d bar n transpose A times d bar n. Okay, so I said I may not write over bar, but it appears I'm able to remember and write it everywhere. So I think that is good. So we have all these vectors with bars, and then the scalars do not have the bars like beta n and alpha n. Okay, so this is the value of beta n. So if I can calculate beta n from the new residual, that is R bar n plus 1, right? From R bar n plus 1 and from Dn, which is the previous direction, then I can calculate what is Bn, beta n. So once I calculate beta n, I can calculate my new direction. That is going to be, because Rn plus 1 bar is known, beta n is known, the previous direction is known, I can calculate what is d bar n plus 1. Okay, so that is the new direction which we can calculate. Of course, I can now try to simplify this thing. So for Rn plus 1 bar times A times Dn, I can go back to this equation, equation 2. Okay, so I'm going to copy paste this equation 2. Okay, and then write my Rn plus 1 bar from equation 2. So paste here. Okay, so this is what I have from equation 2. So I can write Rn plus 1 bar equals Rn minus alpha A dn. Okay, so let me write from here what is the value of minus A dn bar. Okay, from equation 2. Okay, so minus A dn is going to be 1 by alpha n R bar n plus 1 minus R bar n. Correct? That's what I have. Okay, so I can substitute for A bar dn here with a minus. Okay, from this equation that I have written, equation 2, that's going to be 1 by alpha n, this quantity. Okay, fine. And then let me go to the equation 3. Okay, let me say, so this is the equation 3. Okay, I'll come back. Okay, so what I have is I'll paste my equation 3 here. Okay, so what we have is from equation 3 we have, so we have this quantity. This quantity is dn transpose A dn. Okay, so I want to write dn transpose A dn times alpha n. Okay, so this is going to be alpha n times dn transpose A dn equal to Rn transpose d bar n. Okay, so that's what I have written. So why did I multiply with alpha n? Because when I'm going to take the numerator, when I substitute for minus a dn to be this quantity, I have an alpha n. This alpha n will basically become in the denominator alpha n dn transpose a dn. So I can combine these two and then write an expression for beta n. Beta n equals, so what I have is Rn bar transpose. Okay, let me write it one by one. R bar n plus 1 transpose times minus ADN, I'm writing it as 1 by alpha n. 1 by alpha n, R bar n plus 1 minus R bar n. Okay, that is from this equation. Okay, and then in the denominator, I have dn transpose ADN. Okay, let me leave it like that for now. So this is going to be dn transpose A dn. Now essentially this alpha n comes down, right? So essentially what we have is we have Rn bar n plus 1 transpose R bar n plus 1 minus R bar n divided by what I have is alpha n dn transpose A dn. Excuse me. So alpha n dn transpose A dn is nothing but Rn transpose dn. So that's what I'm going to substitute now. So my beta n is going to be R bar n plus 1 transpose R bar n plus 1 minus R bar n divided by R bar n transpose dn. Okay, so we have R bar n transpose dn. Okay, let me now try to simplify this further. So beta n is going to be, so I multiply with this quantity. So we have R bar n plus 1 transpose R bar n plus 1 minus we have R bar n plus 1 transpose R bar n. Okay. Okay. I don't need to write these parentheses actually. Okay. So could not, these need not be written. Okay. So this is required. Okay. That is the numerator divided by, we have R bar n transpose D bar n. Okay. What do we know? We know from the steepest descent method, or even we know that residual at n plus 1 is always perpendicular to residual at n. So this quantity is equal to 0. So what I have is I have an expression for beta n that is equal to R bar n plus 1 transpose R bar n plus 1 divided by R bar n transpose D bar n. Okay, that's what we have. Let me try to even reduce this further. R bar and dn. Okay, so we have what is dn? So we said dn plus 1 equals Rn plus 1 plus beta n dn. So let me recast equation 4. Let me rewrite equation 4. Okay, to try to simplify this further. Okay, let me recollect from equation 4. What we said is the new direction dn plus 1 equals d bar n plus 1 equals R bar n plus 1 plus beta n dn. Okay, so I can write this for d bar n instead of d bar n plus 1, right? Then in such case is going to be R bar n plus beta n minus 1 d bar n minus 1. Okay, that's what I have. Then I can now evaluate the denominator here, which is Rn transpose times d bar n equal to Rn transpose times R bar n beta n minus 1 d bar n minus 1. Okay. Okay. So this is going to be R bar n transpose R bar n plus beta n minus 1 times R bar n transpose d bar n minus 1. Okay. But what is R bar n transpose d bar n minus 1? Right. So now I'm basically now looking at Rn transpose and d bar n minus 1. So we have also proved this thing that before, slightly before. Yes. So not here. Before this one. So here. So we have proved that Rn transpose Dn. So Rn plus 1 Dn is equal to 0, right? This is what we have proved. Okay, let me copy paste this guy. Okay, that means the residual at n plus 1 is orthogonal to the direction Dn. Okay. So let me put that here. Okay. So what we have is, this is what we have from the previous calculations. Okay, so we have from previously established. So I can write this for one step before this as by changing r bar, by changing n plus 1 to n, and then dn to n minus 1, right? I'm just replacing n with n minus 1, which is going to give me n here and n minus 1 here. Now this should also be equal to 0. This is nothing but this is exactly the same quantity we have in the previous term here. So that means this entire thing, beta n minus 1, this entire thing goes to 0. So my quantity Rn transpose Dn is nothing but Rn transpose Rn, right? So R bar n transpose times D bar n is nothing but R bar n transpose times R bar n. Okay, so that is the denominator which we have simplified. Now I can go back and plug in these two, wherein for beta n, the numerator is simply Rn transpose, Rn plus 1 transpose Rn plus 1. Denominator is Rn transpose Rn. Okay, so I can write my beta n is equal to R bar n plus 1 transpose times R bar n plus 1 divided by denominator is R bar n transpose times R bar n. Okay, so that is my beta n. Okay, now we are able to calculate everything, right? So we calculate what is alpha n, we calculate what is beta n, we calculate what is dn plus 1. So we have calculated everything, right? So that means we are now ready to write the conjugate gradient algorithm. So the CG algorithm goes like this. First, calculate your residual at 0, right? That is the 0th step. That is, we take the residual direction to be same as the conjugate direction d0. This is going to be b minus a phi 0. Okay, so this is basically the initial residual. Also, the same as the conjugate direction. Okay, so once I know R0, I can calculate what is alpha n, right? Alpha n is nothing but, if you remember, we have alpha n expression, Rn transpose Dn by Dn transpose A Dn. Okay, so I know what is Rn, what is Dn, so I can calculate alpha n. This is Rn transpose Dn divided by Dn transpose A Dn. Okay, so that is my alpha n. So once I know alpha n, I can actually calculate what is phi n plus 1. Phi n plus 1 is nothing but phi n plus alpha n dn. Because I know dn, I know alpha n, I can calculate what is my new guess for phi n plus 1. Okay, all right. So, okay, now what you notice here is that already this is different, right? This was different in the steepest descent method. Okay, all right. Now we have phi n plus 1, but then how do I proceed to the next value of dn plus 1, right? To do dn plus 1, I need what is beta n, I need what is Rn plus 1, and so on. So, but my beta n calculation requires Rn plus 1, so I can calculate what is my R bar n plus 1, next R bar n plus 1. That is nothing but, we have already written it here somewhere. R bar n plus 1 equals R bar n minus alpha n a dn. So I can write this. R bar n minus alpha n a times dn. So we already know what is alpha n. We know a, we know dn, we know Rn. So I'm able to calculate the next residual. But then once I know the next residual, I can calculate what is my beta n. Beta n equals R bar n plus 1 transpose R bar n plus 1 divided by R bar n transpose R bar n, right? We have just calculated this here. So this is the same expression which I have written. So once I know beta n, I can now calculate what is my new search direction. That is d bar n plus 1 is nothing but residual at n plus 1 plus beta n dn. Okay. That is the new search direction. So once I know dn plus 1, essentially I go back here, right? I substitute for new dn plus 1 here. And then I'm going to substitute for dn plus 1, rn plus 1 I already know. I calculate alpha n plus 1 with alpha n plus 1, phi n plus 1, dn plus 1, I can calculate phi n plus 2. And then the cycle repeats. Okay, so essentially, so what we're doing is that, so here, iterate till convergence. Okay, so everything that is below, we iterate till convergence. Okay, so essentially go to step 2, if not converged. Okay. All right, I think that is the, we finished the conjugate gradient algorithm. That is little intense compared to the steepest descent, because steepest descent was much more straightforward. Comparatively, in the conjugate gradient, you have to now calculate this new direction d, from the residuals, and then subtract off the direction that is in the direction of Rn, in the direction of dn already. Okay, so that's what we have already subtracted off. Fine. Okay. Okay. Let me show you an example of this thing. Okay, together with the steepest descent method. Okay. Any questions so far? Please ask me. Something else. Okay. Do you see my screen, MATLAB screen?
Yes, sir.
Yeah.
Yes,
Okay. Okay. Is the font okay?
yes, sir. It is visible, sir. Very visible.
Okay. Okay. So what I have is so this is the same steepest descent method code that I have shown you in the last class. But then I made some small changes instead of, so that I can, essentially run it at different sizes of the matrix. Okay. So what I have said is n equals 2. Here I'm looking at a 2 by 2 system. A equals zeros of n by 1. That is basically a 2 by 2 zeros, and then B is ones. Okay. Then, so essentially we want to build a symmetric positive definite matrix for any size that we take. For example, 2 by 2, 10 by 10, 1000 by 1000. We always want to ensure that this A matrix is symmetric and positive definite, and then we want to take some B side matrix. Okay, and then hopefully there is some solution. So that is what I am trying to do. So for that, what I have done is first I generated some random matrix. So random of n will generate n by n matrix with random numbers. Okay, so essentially random numbers. But then if I take, if I multiply that random number matrix R and R transpose with R, then that's going to give me a symmetric and positive definite matrix. Okay, a symmetric matrix. And then to make sure that it is positive definite, I basically increase the diagonal values by this n value. Okay, that means E by I basically gives you an identity matrix in MATLAB. So that identity matrix I'm multiplying with n, that is the size, and I'm adding it to A. Okay, so essentially these two steps will ensure that this matrix A I'm getting is symmetric and positive definite. Okay, this condition is required, otherwise none of the steepest descent or the conjugate gradient will work. Okay, and then the B matrix also I'm taking it as random matrix of one column vector and then n rows. So this is n by 1, this is the column vector. And then X and R, this is the solution, and then the residual, and maximum number of iterations I'm taking it as 10. Okay. And okay, this was the what we had in the last lecture. This is the A matrix and the B matrix that we have seen, which I have now commented out. Okay, and then I take my residual 0. I'm kind of copying it residual into residual 0, and then I open a file called output vector standard. Okay, so this is coming from the steepest descent method, std, and then I'm writing what is the value of x. Okay, so this is my value of x, and then I perform the steepest descent method. What was steepest descent method? Perform several iterations, 10 iterations. Residual equals b minus ax, numerator equals Rn transpose Rn, denominator equals Rn transpose A times Rn. Then you calculate your alpha, which is Rn transpose Rn by Rn transpose A Rn. Then you calculate your new x. So this is so simple. Xn plus 1 equals Xn plus alpha times Rm, right? This was the steepest descent. And then once you're done with new Xn value, you are updating your old x with Xn, okay? Then I'm also displaying R and I'm also writing it to the file. What is the new X value I have found? Okay, this is the new X value. And then I'm also storing R0 for previous residual for later use. And then once I'm done with all iteration, I'm closing the file. And then I'm printing what is the error. And then I'm printing the norm of the error because error itself is a vector here. Okay, fine. So that is what I have. Let me run this thing. Let me run this. Okay, so it has converged in 10 iterations. It has given a norm of 7 into 10 power minus 7. Okay, so it has given a norm of 7 10 power minus 7, which seems to be already quite small, but it has taken 10 steps. Okay, I've done 10 steps as such. Okay, then it has also written some data to this file, which is called output vector standard.txt. Let me open that file. Okay, so enable. Why is it not able to open this? All files. And it should open. This text. I don't know why it is not opening this. Anyway, I can just open it. If it is not able to open, I can open it as a separate file. Okay. What is this is? Okay, output vector standard. Okay, I think this is now a little bit too small. Okay, so it has written something like this. Okay, so what we have is basically it has written all the x values we have taken. Okay, now what I want to do is I want to plot all these x values and then see how it is searching. So for that I'm looking at this slightly different another MATLAB code, which is basically it is loading output vector standard.txt, which is exactly the same as this file. Okay, this file it is loading. This is the x values. Okay, and then column 1 contains the x coordinate, column 2 contains the y coordinate. It is just plotting it. Okay, let us run this and see. Okay, you see this figure. What do we notice? Okay, I made this figure bigger. So what you notice is that it basically starts from 0 0. That is my solution. It goes in this direction, then it goes in this direction. Then you see the third direction is again parallel to the first direction, right? And then you see that fourth direction is again parallel to the second direction. And if you were to zoom in here, okay, so if I were to zoom in, again the next direction is parallel to this one, and this is parallel to this one, and so on. So it's basically doing, it's searching in the same directions multiple times, you see? So it's doing the same thing, and then eventually it comes to this solution. Okay, this solution is some 0.118 and minus point something. Okay, it's done that, but it is basically searching in the same direction multiple times, which is what we want to avoid. Okay, because that's why it is taking several iterations. Okay, is this clear, this part?
We will review and get back to you, sir. Yeah.
Okay. So let us look at the conjugate gradient method. So what I have is, again, I have pretty much the same code as before. N equals 2, A, B, everything. But then I'm doing n max equals 3. I'm doing only 3 iterations. Ideally, it should converge in n steps itself. Okay, conjugate gradient will converge in n steps if n is the size of the matrix and n is the number of directions we are taking. Okay, so I just put 3. And I have the same code here. I'm generating a random matrix. I'm taking random transpose times R, and I'm adding it to the identity matrix. And then I have the B, which is the random matrix. Then I'm calculating what's the residual. And here I'm taking the first search direction, that is D equals R. That means D0 equals R0. And again, I'm opening a file. This file is output vector cg.txt. Instead of std, steepest descent, I have cg.txt. And then I'm writing the new x value. Then I come to the conjugate gradient method. This method is you iterate till convergence, calculate numerator. Numerator is dn transpose times Rn divided by dn transpose a dn, that is my alpha n. Note this is different from the steepest descent value. Then my xn plus 1 equals xn plus alpha n dn. Okay, that's what we calculated. Then my new direction alpha r1 is going to be r minus alpha times a dn, right? New residual. Then my numerator is Rn plus 1 transpose Rn plus 1 divided by R transpose Rn transpose Rn. That is my beta. Okay. Once I calculate beta, I can calculate the new search direction D1 equals R1 plus beta times T, right? Dn plus 1 equals Rn plus 1 plus beta and Dn. That's what we have written. And then my new x is copied to the old x, and my new residual is copied to the old residual. And then I'm printing what is x, okay, what is the search direction. And then I'm displaying these two and then closing it, calculate the error and display the norm of the error. Okay, let me try running this code. Okay, so I think it didn't print the error norm. Where is error norm? Display final error norm. Why is it printing two values here? It should have printed the. Okay, final error norm is, you can see this is 1e minus 16, okay, which is much smaller than what we had before. Okay, so let me, so it has also written a file that is output vector CG. Let me open that file. Now that is this file, okay. This file is like this. It has basically just 1, 2, 3 steps after 0, 0, as we guessed, because it just takes 3 steps to do this thing. And then I'll open and I want to plot this. Plot residual underscore CG, that is the conjugate gradient residual. So if I run this one, okay, we see just 3 steps and none of them actually repeat. So it starts with 0, 0, it goes this way, and then it comes back and then it just shows you the final answer, right? Minus 0.02. So, okay, what you notice that this solution is not exactly same as the previous solution because I have used random matrices. So I'm not solving for the same matrix. That's why you will see that this final coordinates are not same as the previous coordinates. But nonetheless, it is giving you an answer. But then you have taken just 3 steps. Okay, so this is step 0, step 1, step 2, and then it has already converged here, right? And it is not taking any direction that is you know, in the same direction as it is. Okay, now of course I can take more iterations. Even then it should not actually take you know, take any this thing. It should not go in the previous direction as such. So I can do maybe make it 5, run this thing, and then plot residual, run this thing. Okay, so it still just basically takes only 2 steps. After that, it doesn't really, it has already converged, right? So it doesn't take anything that is again in that direction. Okay, one thing we can do is, of course, we can also test the steepest descent method, but then I won't be able to plot if I increase this n to something like, you know, I can always solve 100 by 100 matrix with, let us say, 100 iterations, right? And then run this thing. So it has a norm of 2e minus 4, right? The steepest descent in 100 iterations, 100 steps of a 100 by 100 matrix is giving a norm of 2e minus 4. Whereas the conjugate gradient, if I make it 100 dimensions, but 100 dimensions we cannot plot, right? We can only, just excuse me 1 second. Okay, so okay, so 100 by 100 we cannot visualize, right? 100 dimensions, but then let me put 100 by 100 and 100 here for the conjugate gradient. Let us see what will be the norm of this. So the previous one was 2e minus 4. This would be how much? Oh, I think it's printing. Oh, okay. So it is, you can see final error norm is 3 minus 15, right? This is much smaller. That means it has already converged in 100 steps. Okay. So that is, but then of course you would need a lot more iterations to bring it down to this value in the case of steepest descent, right? Because steepest descent was only 1a minus 4. Fine. I'm going to share all these files so that you can also play with them and then learn. Okay. So that kind of finishes the conjugate gradient method and the steepest descent method. Okay. So that finishes the steepest descent and the conjugate gradient methods, which are both of the gradient type methods. Okay. So tomorrow, let us look at the solution to parabolic equations. Okay. Hopefully either tomorrow or the day after tomorrow, we should be able to wrap up the syllabus.
Sir, one question.
Yeah.
Sir, regarding assignment 4, can you give some brief explanation about the sums and then we can be easy for.
So sorry, say it again. You want me to just explain how to solve, go over the problem?
Yes.
Okay. I'll do it tomorrow.
Yeah, it's okay. Sir, similarly, after end of this fifth chapter, can you give some workout samples, examples for chapter 3, 4, and 5? Then it will be better for doing some hand calculation for practice.
You want some practice problems for chapter 3, 4, and 5, huh?
Yes.
Okay. I'll see if I can give at least 1 or 2 problems from each chapter. I'll see. Okay.
Yeah.
Okay. We'll do that. When is the assignment due? This one?
Sir, coming 4th.
4th. Okay. So actually we have one more assignment for the assignment 5, which is on the PDEs. Because your exam is not until 20th. I'm wondering if I can give one more assignment. Let us say you submit by 1 week from now. Let us say from 4th to by 14th or 15th. Do you think you'll be able to submit if I give one final assignment, assignment 5?
Yes.
Yeah.
Sir.
Okay. Yeah. Fine. Then we will just have another assignment. Maybe by tomorrow or day after, I'll post it, and then you can submit that as well. Because that will prepare you for the exam also. See, essentially these assignment problems are your practice problems. Together with that, I can give few more problems, for practice.
Sure, sir.
Okay. All right. Anything else, anybody?
Sir, just one question actually, like on this conjugate gradient
Yeah.
method as well as the steepest
Descent.
descent method.
Yeah.
So it is very complex, but do we just on the curious, like do we expect any problems in the exams related to this one, sir?
So for example, I don't know whether we expect problems or not, but I have done one problem on steepest descent, the other day. We solved an example problem. So, essentially the algorithm is there. If it is asked, you will be able to do it, yeah. So that means it also tells you that you should type up this algorithm, or else I'll give you, if at all I'm going to ask you, I'll give you the algorithm in the question paper itself. So that you can, follow the steps and then maybe do one iteration, just to know that how it works.
Okay,
Something
sir.
like
Okay,
that,
sure.
right?
Sure.
Yeah.
Thank you, sir.
So, but then of course, if you look at the algorithm, it is only 6 lines or 8 lines long. If it is steepest descent, just some 4 lines long. Conjugate gradient is some 6, 7 lines long. But then that doesn't tell you what it is actually doing. It gives you a bunch of matrix vector multiplications and then vector updates. But to understand what it is actually doing or what are its limitations, we have to go through this entire thing. Like what we have done in today's lecture. What is this new direction? How is it trying to calculate and so on?
Sure, sir. Sure.
Yeah,
Sure.
yeah,
Thank you, sir.
Yeah. Also, I think I would need your formula sheets. Maybe by, let us say, by next Monday or something. Can you send me the formula sheet, whatever you want to be included in the question paper?
Yes.
Yeah.
Yes, sir.
Okay, you can. Yeah, you can nicely type it up or something so that it is readable by everybody. Yeah, maybe 2 pages. 2 pages, and then just send me by Monday.
Thanks.
Okay, yeah. But anyway, you can, I'll include that formula sheet, whatever you want to, but wherever it is required, I will give all the required stuff in the question paper itself so that you don't have to really look at the formula sheet as such. Okay, we'll do that. Yeah. All right. Okay, guys, I'll talk to you tomorrow. And then we will look at the assignment problem and then look at parabolic equations and then see either if we can wrap up tomorrow or by Wednesday. Fine. All right. Thank you, guys. Talk to you tomorrow. Bye-bye.
Thank you, sir.
Thank
Thank
you.
Sure, thank you.
Thank you. Thank you. Bye.
Thank you, sir.
Thank you, sir.
Thank you. Thank you. Bye.
Thank you so much, sir.
Sorry?
Thank you so much, sir. I just said.
Thank you. Thank you. Yeah. Thank you, Aditya.